What we want to do now is think a little bit more what a construction is, the steps that we take, and what that means about the objects that we end up with. So remember in the last video we ended by talking about the various steps that a construction involves, and it involves basically drawing lines and circles and finding intersection points of those things. So we want to now look at the algebra of that. So we want to think about the actual physical construction and tie it to some algebraic expressions. So here's where we're going to start. We're going to start by saying a point a comma b is constructible when the lengths a and b are constructible lengths. So remember when we did some constructions, when you did that for homework, you would choose a unit length, and then you could make length 2 and length 3, and you could make lengths, I think you made a 5/3. So we could make any rational length using those steps. So a and b are lengths that you can construct. It means you can make the point a comma b on a plane. Okay, so we're going to be thinking about, we want to think about something like, so if f is some field of constructible points, and you should be thinking, for example, like maybe f is q, then what we're thinking about is a and b, the lengths are in that field f. Okay, and we can think about f as q, and then we want to know, is f bigger than that? What are the things that are in f and what are not? So the first question is, when we draw a line through 2 points, what does that mean about the line? So we call a line constructible if the 2 points that it's drawn through are constructible. So A, B, C, and C, D are constructible. So what that means is A, B, C, and D, those variables are all in F. Okay, so what does this mean about the equation of the line? So the line through A, B, and C, D, if we do, I think this is point slope form maybe, we write it as y minus d is, the slope would be d minus b over c minus a times x minus c. That's the equation of the line through those points. And if we rearrange it a little bit, we're going to rearrange it so that it's set equal to 0 on one side. What we get doing that algebra out is d minus b over c minus a times x minus 1y plus d minus cd minus cb over c minus a. Okay, so this is just solving all to one side and equal to 0 on the other side. So we want to look at that equation and think about a way to describe it. So we're going to look at those coefficients. So d minus b over c minus a, minus 1 is a coefficient, d, and this minus this big fraction, those are the coefficients of our line. And what we're going to notice about those is because A, B, C, and D were in our field F, F is closed under addition and subtraction, multiplication, division, and so all these coefficients are in F. Okay, and now there's one thing that we didn't really consider here, which is this equation works fine as long as C doesn't equal A. So if C happens to equal A, that means we have a vertical line. Then our equation is just x equals A instead of this whole thing. There's a undefined slope. So our equation there for the vertical line is just x equals A. But still, even if it's just x equals A, those coefficients, the A and the 1 times x, are in F. All right, so what we know now is that if a point is constructible, it means the x-coordinate and the y-coordinate are constructible real numbers. If a line is constructible, it means that all the coefficients of the line are in the field, so they're constructible numbers. For circles, we're going to use a constructible point, AB, and a constructible radius, R. that gives us a constructible circle. And so again, we want to know what does this mean about the equation of the circle. So are all those coefficients in f again, or is there something more we can say? So the circle through with center AB and radius r is x minus a squared plus y minus b squared equals r squared. And so again, if we solve this so that it's all set equal to 0, what we get is x squared plus y squared. And then we have a minus 2ax minus 2by. And for a constant term, we have plus a squared plus b squared minus r squared. All that is set equal to 0. So we're just looking at this equation again and asking ourselves, just like above, what can we say about the coefficients? So the coefficients here are 1 in front of the x and the y. We have a minus 2a, a minus 2b, an a squared, a b squared, and r squared. All coefficients, again, are in f because a and b and r were all constructible lengths. Okay? So all the circles and lines we draw have coefficients that are in that field of constructible numbers that we started with. So now we want to start thinking about intersecting these things. If I intersect two equations where all the coefficients are rational numbers, for example, is the intersection point a rational point? Are the coordinates of the intersection point rational? So what we're thinking about is, e.g., if f is q and we intersect two lines with rational coefficients, is the intersection point rational? Does it have rational coordinates? And what about if we intersect a line and a circle? Is the intersection point going to have necessarily rational coefficients? Or at some point do we end up with things that aren't rational numbers anymore? So we're going to just do some algebra with those equations to answer this question.